Right. We're looking at the fields from various arrangements of static charge. We talked in the previous lecture about the field from a point charge, and today we want to deal with the field from a dipole. And so we first need to figure out what a dipole is. And a dipole is a pair of charges, um, equal magnitude, opposite sign, and this then is a dipole. There is a distance d between the dipoles, which is referred to as the dipole moment. What we want to do today is to find out what the field is at a point P that is on the axis of the dipole. And we will assign the variable z to the distance from the point halfway between the two charges, 2p, so the field, well, it is just going to be a matter of adding up the fields from each of the point charges. You have the principle of superposition at play, so the field would be the sum of the field from the positive and the field from the negative charge. Note that those fields will be in opposite directions, so when we add them it will be a subtraction. That we recall Coulomb's law, and so the field is going to be 1 over 4 pi epsilon times the positive charge, which I'm just going to look at the magnitude of, and the distance from the positive charge to P, which we call R plus. I'm not using Z yet, squared, and minus the field from the other one. And notice we don't put in the positive and negative here because we've already captured the effect of that by this subtraction right here. Now, that distance from the positive there would be z minus 1/2 d, and the distance from the negative would be z, oops, we lost it, z plus 1/2 d. And how do you deal with that? And to deal with that, we're going to do a binomial expansion. This is a two terms raised to a power, and so that is a binomial, and we will do an expansion, and you may or may not recall, I am just working with this one here, and then we will wave our hands at that one there. But this term 1 over z minus d plus 2 raised to the second can be also written as z to the minus 2 times 1 minus 2 over 2z raised to the minus 2. That's nothing magical happened there. Now comes the magic. I'm going to take this expression here, and I'm going to do a binomial expansion on that part of it. I think I'm going to need more room. And you may recall that that is this raised to that power plus a negative 2 times this raised to this power minus 1, and this raised to this power plus 1. It looks like this. Come on now. Okay, so this was 1 raised to the minus 2 minus 1, and this is minus d to the raised to the first power. I'm sorry, not to this plus 1, but to the first power. And the next one would be this term raised to the second, and this raised to the minus fourth. The coefficient that goes out in front, you've got to use the, what's it called, the factorial, a ratio of factorials to get this coefficient. And it's kind of tricky with negative numbers, so I just don't know what to do there. But that's okay, because this term and all the subsequent terms I'm going to get rid of. If I make the assumption that this distance z is much greater than this distance d, then, come on now, then this term here sticks around. 1 raised to the minus 2 is just 1. And this term here, I'm going to have it stick around. Even though z is much greater than d, you might legitimately say that goes to 0, but then I'd lose all my information. So it's not convenient for me to make that term go away. But this term here, when I'm squaring d over 2z, if z is much greater than d, then this term I am going to say goes to 0, and so I don't have to deal with that awkward coefficient. Or any of the subsequent terms, which are going to be this raised to the third and this raised to the fourth. So I'm just left with this, which I simplify to be z to the minus 2, and take that 2 and this 2 and put them together, and that minus and this minus, and you get this expression here. Excuse me. So this then is equivalent to this term right here, and this term here is going to look just like this, except it's going to have a minus instead of a plus there. And if you don't believe me, then go through all the work that I just went through. And so this thing here can now be written as q times, and this term here would be replaced by that term, and then this term here is replaced by this term, and then I can start to work with that you can see that I have z to the minus 2 minus z to the minus 2, so boom, that's gone. And then I have z to the minus 2 times d over z minus z to the minus 2 d over z. So I have two of those, z to the minus 2 times d over z. And then I'll pull the d over z, z to the minus 2 down here with this one, and I am left with this expression, which does describe what the field strength is at this point P, a distance z from the dipole. We would say that this location, this sort of center of gravity of the dipole, or center of electricity of the dipole, is the location of the dipole right there. And so here is an expression. But we go further with this. I'm going to take the come on now. I'm going to take this q times d, and I'm going to replace that with the letter p. And this is called the, I think I might have called that the dipole moment. But p, this q times d is what is known as the dipole moment. And so this whole thing can now be written as 1 over, notice this 2 and the 4 on the bottom, so you end up 1 over 2 pi epsilon p over z to the minus 3. Not z to the minus 3, z to the third in the denominator. This is an expression for you to memorize. And you can at least get the units right by realizing that this has dimensions. It's got dimensions of distance in it. And here you've got distance to the third, so we end up with charge over distance squared, which would be the dimensions we would expect for the field strength. Point here it is again, the expression for the field strength, that this value, the dipole moment, it is a vector quantity, and its direction, according to our conventions, is the direction a positive would go, but very important, the direction a positive would go outside of the dipole. So if this top charge is positive and the bottom charge is negative, then the up here at P, a there would be a net upward force on a positive charge. Down here below, if you put a positive test charge in here, there would be a net upward force. Of course, in between the two, if you put a positive charge, it would be repelled by this positive charge and attracted to that. And so the arrow would go down in between. When we talk about the direction of a dipole, the dipole moment, we always are going to be talking about the direction outside, not between the two. This expression that we got only works on the axis of the dipole. Could be up here or could be down here, but it's only on the axis. If you go off the axis, we do not have an expression, at least not an easy one. And you will have situations where you will be asked for the field strength at some point out here, and you just have to bash it out by adding those two forces together. But it is the case that off the axis the field does vary as the distance squared, cubed, inversely as the distance cubed. So that is a useful thing to know. As you go away from a dipole, this distance cubed is going to cause the field strength to go to zero much faster than the field strength goes to zero from a point charge. That is, when you get far enough away from this pair of charges, the net charge here is zero, and we would expect it to look like a no charge at all. And it gets to looking like that much more quickly than when you go away from a single point charge, where the field strength does fall off, but as the square. And that concludes this lecture.